Our two types of charge are positive and negative charge, as we talked about on Friday. Can you tell me what the difference between positive and negative charge is? We're talking about objects here, right? Not individual charges that make up positive and negative charge, but the objects themselves. Ollie?
More protons than electrons.
All right. So positive has more protons than electrons. It doesn't mean that there's just protons. Of course not. Every object that makes up matter or that is made up of matter consists of both protons and electrons and also neutrons. But it has more protons than electrons for whatever reason, as opposed to a negative charge, a negatively charged object, which is an object that has more electrons than protons. So if we've got something that is neutral and it loses electrons, and it's going to be electrons, by the way, that are transferred, right? How come? Why is it electrons that move as opposed to protons that move? Yeah, they're the thing that's in the outer part of the atom. They're not as tightly bound to the nucleus. There is an electric force that pulls them in to the nucleus, but it's not nearly as strong of a force as that strong nuclear force that keeps the nucleus together. Now, it is possible for a proton to leave the nucleus, but that's a nuclear reaction. That's not a normal electrical interaction that we're talking about here. So it is going to be electrons that move. If an object loses electrons, which can happen quite easily by rubbing a balloon against your hair, then the object that loses electrons becomes what? Positive or negative? The one that loses electrons becomes, Rosie? Positive. If something loses electrons, then something else has got to gain electrons, right? Because they got to go somewhere. That thing that gains electrons becomes negative, right? That's how we get positive and negative charged objects. A little bit later today, we'll talk in more detail about how to charge something positive or negative, how to give it that charge. But in essence, that's it. What are the units for charge? Ollie? Yeah, it's C, or named after the actual units are the Coulomb, but which is named after a guy named Charles Augustine de Coulomb, but the symbol that we usually give for that is a capital C. Yep. Good. Big unit or small unit? It's a big unit, right? In fact, we saw that it took about 10 to the 19 electrons or about 10 to the 19 protons in order to make up a Coulomb of charge. So we often see coulombs or charge listed not as coulombs, but rather as millicoulombs or microcoulombs or even nanocoulombs. 10 to the minus 3 coulombs, 10 to the minus 6 coulombs, 10 to the minus 9 coulombs. If you think you might forget these prefixes, by the way, don't worry about it. They're on your data sheet. Just know where to find them on your data sheet. Anybody remember what the charge of an electron? By the way, the symbol for charge, the unit for charge is the Coulomb. The symbol is a lowercase q. Does anybody remember what the charge of an electron is? Find it on your data sheet. If you don't remember what the charge is, and you probably don't, that's okay because you don't have to memorize it. Find it on your data sheet and tell me what the charge of an electron is. Chase? Yeah, it's -1 times the elementary charge. And on your data sheet, you'll see that the elementary charge is 1.6 times 10 to the minus 19 coulombs. So we'd say that -1e, the way it's listed on your data sheet, is really -1.60 times 10 to the minus 19 coulombs, as opposed to a proton that has a charge of +1e, or in other words, we'd make that positive 1.60 times 10 to the minus 19 coulombs. Now, we don't pay a whole lot of attention to the mass of these things because we're talking about electricity, and it's the charge that's the most important property of these particles. But if you did look at the mass, which one would be heavier, proton or electron? Proton, dramatically heavier, right? Somewhere around 1,000 times heavier. Neutron is about the same mass as a proton, give or take a little bit, right? Pretty much. The 3 significant digits is the same mass as the mass of a proton. Good there? 2 more terms. Conductor versus insulator in the context of electricity. What's the difference between those? If you can't think of what the difference is, try to think of an example of a conductor and an example of an insulator. No one? An example of a conductor would be metal. Good. The general category for conductors is usually metals. Yeah. And can you tell me why, somebody? Metals tend to be better conductors than... No one, what's an example of an insulator? Okay, rubber's a great insulator or a poor conductor. Okay, what's the difference between metals and rubber, or metals and wood, or metals and plastic, Rosie? Good. Um, the electrons in the outermost regions of any atom can move, but the electrons in the outermost regions of a conductor are much more free to move about. And because they're more free to move about, then we can get those electrons moving from one place to another. In other words, we can get conduction taking place, right? We can get movement of charges taking place. So conductor is something that allows electrons to transfer, and that's because it has the electrons in the outermost regions pretty free to move about. And that generally occurs in metals, as opposed to insulators, which is exactly the opposite of that. The electrons aren't as free to move about. And some examples of that, as Nolan said, would be rubber. Okay, a perfect example of it. Glass, plastic. Okay, basically, we're talking about non-metals. Varying degrees, right? Okay, we talk about an insulator. We're not saying it doesn't conduct at all. It does. We're talking about a conductor. We don't say that it doesn't insulate at all. It does. But it's all relative. These are very, very poor conductors versus good conductors. All right. Finally, on Friday, we left off with 3 laws of electric charge. In fact, I think we only left off with 2 of them, because I don't think we actually got to the third one. First one we said was opposite charges attract each other. By opposite, we mean positive, negative, right? Something's positive, something's negative. Positive charge attracts negative charge. Negative charge attracts positive charge. Do you guys know what attract means? Like in the context of charges, that is? Some of you are thinking, yeah, in grade 6, there was this girl. Man, I was attracted. No, that's not what we, well, kind of that's what we mean. Kind of, I guess. If you're attracted to something, you're pulled towards it. Okay, 2 charges are attracted to each other, then positive will pull negative towards it, right? Okay, pulled towards. As opposed to like charges repel each other. You know what repel means? Well, in grade 6, there was this girl that found you repulsive. Never mind. So that girl that you were attracted to, repulsive means that pushed away. So as you're attracted to her, okay, she is repelled by you, and is pushed away by you. Maybe, no, that wouldn't be the case for you guys at all. For the other class, it might be, but not for you guys. Like charges repel each other. Positive repels positive, negative repels negative. The third law, which we didn't talk about on Friday, I'm going to give you the law right now, and then I'm going to explain to you a little bit later on why it's the case. These are what I would consider to be fundamental laws. These happen because they happen. The third one happens because of something else. Charged objects attract neutral objects. Charged objects attract neutral objects. So what we're saying here is that you got something that's positive or something that's negative, it will attract something that's neutral. Now, neutral doesn't mean positive or negative. Neutral means equal numbers of positive and negative. So how can something that's charged attract something that's positive, but also attract something that's neutral? We'll deal with that again in a few minutes, but what I want to leave you with here with this page is simply this. Okay, remember that charged objects attract neutral objects. That word objects is important. Protons do not attract neutrons. Electrons don't attract neutrons electrically. They don't attract neutrons because a neutron is a neutral particle, not a neutral object. There's a difference. A neutral particle has no protons and neutrons present. It's just no charge. Whereas a neutral object has same charge, neutral, but it's got both protons and electrons, and that's important. Okay, again, you'll see why in just a couple minutes. Christian?
I'm here, Joe.
One more law here, which is kind of separate from the first 3 laws. We call this the law of conservation of charge, which says almost the same thing as the law of conservation of anything else. Conservation of energy can't be created or destroyed. Conservation of matter, Matter can't be created or destroyed. Conservation of momentum, well, we said conservation of momentum was initial equals final, but what does that really mean? Momentum can't be created or destroyed. Conservation of charge says that charge can't be created or destroyed. It can be transferred from one to another, but it can't be created and it can't be destroyed. If I walk across the carpet and pick up a charge on my body due to friction, and then I go and touch your finger, I can shock you. I've transferred charge to you. Electrons have moved to you, but we haven't created anything or destroyed anything. The total amount of electrons that exist in that system is exactly the same as it was before. It's just that now they're rearranged. What's happened to the protons in that interaction, by the way? When I walk across the carpet and touch somebody and shock you, what's happened to the protons? Nothing. Protons stay where they are. What's happened to the electrons? They're the ones that have transferred. Now, this law of conservation of charge manifests itself in a whole number of ways. Okay? All kinds of different things, from subatomic interactions to big interactions between the balloon in your hair that we keep going back to even bigger interactions between clouds and the ground when lightning forms. All kinds of places where it manifests itself. But we're going to give you one fairly simple place right now, and that is when two things that have charges touch each other, or in this case, I guess, three things that have charges touch each other. Before we copy this down, let me just give you the idea behind this here. If I've got two things that have different charges and I touch them together, then the goal is always to balance out those charges. Now, it doesn't always completely happen. It depends upon the size and the shape and the material of the objects, but we'll assume whenever we do questions like this, if the size and the shape and the material are close enough to each other, that the charges will balance out. Now, you can imagine if I have one object that is a small sphere and then one object that is a massive sphere, then the one that's a massive sphere will hold more charge than the one that's small. Right? But we're going to assume that when we do questions like this, that they're all the same. So that when I touch a ball number 1 with a charge of 3 coulombs, which is a really big amount of charge, to another one that has a charge of -1 coulomb, and then I touch the first one to a third one that has a charge of -5, then in each interaction there, the charges are going to balance out. How do we figure out what the final charge is on all three of them? So if two objects just touch each other, it's easy to figure out what the charge is going to become on each other, and they just simply balance out. But if three objects are involved in this interaction, then my suggestion would be to create a little table, just kind of a mini table here. We got charge 1, charge 2, and charge 3. They start off as +3 coulombs, -1 coulombs, and -5 coulombs. That's what they are before anything happens. At the beginning of the problem, this is what they are, +3, -1, and -5. Now, it says I touch ball 1 with ball 2. So +3 and -1. If I touch those two together, the total charge remains the same. But what are they going to balance out to be, assuming similar size, similar shape, similar material? It's going to be +1 and +1. How do we figure that out? Average them. 3 plus -1 gives me 2. Divided by 2 gives me +1. So when these two touch each other, it becomes +1 and +1. Right? The total charge between the two of them was +2. The total charge is still +2. What's the third one become? Stays -5 right now, right? Nothing's happened to that yet. Then it says the first ball then touches a third one that's -5. So we've got ball 1 touching ball 3. +1 and -5 gives me a total charge of -4. They're going to balance out to be -2 and -2. What's the second one become? +1. It doesn't change because in this interaction, nothing's happened to it. Now, how would this change if all three of them touched each other at the same time versus sequentially like it did in this question? We don't very often see a question where 3 of them touch each other at the same time. Usually it's 2 at a time. But if they did 3 at a time, Peter, what would we do? Yeah, you'd add them together and divide by 3 in that case, right? Average all 3 together. Here we can't do that because they're not doing it at the same time, right? 1 touches 2, 1 touches 3. It's 2 separate problems, and that's what we did there. I think it's just easier to figure it out when we form a table like that. Does that make sense? Okay, take a look at a multiple choice question right now. Question number 32 in your worksheet booklet, please. All right, let's have a look here. It says 2 conducting spheres have identical surface areas. Why do you think they're telling me that they have identical surface areas? Yeah. No, not so much for friction. What did I say when 2 objects touch each other? They like to balance out. But if they're not same size, same shape, then they can't balance out. Bigger things can hold more charge. They're just telling me here that, look, they're going to balance out, right? You know what? Even if they didn't say that, we still would have treated this the same way. They're just clarifying it a little bit for me. Sometimes it can be confusing, though. When they try to clarify, sometimes it ends up being more confusing. Anyways, these things are going to balance out. It says sphere A has a charge of 4.5 microcoulombs. B has a charge of negative 2.4. They're brought into momentary contact and then separated to a distance of 2.5. What's that 2.5 centimeters? What's the relevance of that? Yep. It doesn't. There is no relevance to it, right? It doesn't matter how far apart they are after they touch together. We don't need to make a table here because it's just 2 things touching each other. All we're going to do is average them out. 4.50 microcoulombs plus negative 2.40 microcoulombs divided by 2 becomes 2.1. Anybody put B? 2.1 divided by 2 gives me 1.05 microcoulombs. So our answer is A. How many people got A? Good. All right, if we can do that one, let's try number 33. All right, so this one asks us for the number of excess electrons when we have a ball that has this amount of charge. You understand that this ball is going to have lots of protons and it's going to have lots of electrons, but it's got extra electrons, excess electrons. We know that because it's negatively charged, more electrons than protons. We want to know how many extra or how many excess electrons this ball has. Well, let me give you a little analogy to help you to figure this one out, okay? Let's say that I go to the grocery store, go to Safeway or Sobeys, and I buy a bag of oranges. And the bag is, I can't see how many oranges are in the bag, but I know that each orange has a mass of 200 grams. Okay, kind of a heavy orange, but let's say it has a mass of 200 grams. When I go to the cash and they weigh my oranges, there's a total mass of 1 kilogram, 1,000 grams. How many oranges do I have in my bag? Each orange is 200 grams. I have a total mass of 1,000 grams. How many oranges do I have in the bag here, Rosie? I got 5 oranges. How'd you figure that out? I said 1,000 divided by 200, which gives me 5, right? Make sense? Everybody can figure that one out. If you can't count the number of oranges, you know that if you know the mass of 1 orange and you know the total mass, then you can find the total number of oranges. All I did was said the total mass divided by the mass of 1 orange gave me the number of oranges. Well, we know the mass of an electron. It's on our data sheet, but we don't know the total mass here. But we do know the charge of 1 electron and the total charge here. The total charge is 3.6. The charge of 1 electron is 1.60 times 10 to the minus 19. That's going to give us the number of electrons. Let's say it's negative 3.60 times 10 to the minus 17 divided by negative 1.60 times 10 to the minus 19. And when you do the division there, you get 225. This isn't any different than the orange question, right? We all intuitively knew how to figure out how many oranges we had. Okay? I got a son in grade 8. Okay? He could figure out, if I asked him the question about oranges, how many oranges were in the bag. He couldn't figure out the number of electrons here, but he could figure out the number of oranges. Really, it's no different. If we know the charge of the electron, then this isn't any different. The logic is exactly the same. Listen carefully to what I'm about to say. Whenever you're asked for the number of anything, number of electrons, number of protons, number of photons, whatever a photon is, you haven't learned that yet, number of whatever, you're always going to take the something total divided by the amount for 1. Might be the total charge over the charge of 1, the total mass over the mass of 1, the total momentum over the momentum for 1, the total energy over the energy for 1, the total something divided by the amount for 1. Make sense? Always. When you're looking for a number, something total divided by something for 1. All right, now we talked a little bit about transferring charge. Touch two things together, the charge balances out. We talked about conservation of charge, and how the total charge remains the same. We talked about how you essentially get a positive charge and negative charge. I want to talk about that in a little bit more detail right now. I want to talk about how to charge objects, give objects a positive charge or a negative charge. Let me tell you first that we break it down into 2 categories of charging, 2 ways to charge objects. One is called conduction, and one is it's called induction. Conduction always involves a charge transfer. And you guys know that if something's going to transfer, if some charge is going to transfer, it's going to be the electrons that transfer. So it always involves electrons moving from one thing to another, always. And it usually involves, not always, but it usually involves touching. So 2 objects touch each other, the charge is balanced out. That's charging by conduction. But it can actually happen before the 2 objects touch each other. For instance, when I walk across that carpet, use the example I used before. When I walk across that carpet and I go to touch somebody on the finger or on the ear or something to try to balance out my charge, try to shock them, sometimes it actually transfers before contact is made. Charges, if the potential difference is big enough, it will jump from one to the other. We still call that charging by conduction, even though it doesn't involve touching, because it still involves a transfer of charge. Charge is going from my finger to you. Okay, it's still a transfer. It's still therefore called charging by conduction. Now we're going to break charging by conduction down into 2 subcategories. Your Physics 30 diploma exam doesn't always make this distinction. Sometimes on our diploma exam, they just have one umbrella category called conduction. But we're going to break it down into 2 subcategories. Charging by friction, and charging by friction involves rubbing. Rubbing 2 things together. When you rub 2 things together, let's say you rub a balloon against your hair. When charges from electrons on one of those objects will transfer to the other object, make one of them positive, one of them negative. The one that gains electrons becomes negative, the one that loses electrons becomes positive when we rub 2 things together. Now, the law of conservation of charge still dictates how this works, right? If I have 2 neutral objects, and I rub them together, one becomes +5, the other one's got to become -5. Because the total charge was 0, it's got to remain 0. So the law of conservation of charge still rules here when we're talking about rubbing 2 things together. The other subcategory is called charging by contact. A lot of times you don't see that separate word, contact. A lot of times this subcategory of conduction is just called conduction. It's called the same thing as its parent category. This involves, we'll say, touching 2 objects together and balancing. It doesn't necessarily have to be 2 objects touching. When I walk across the carpet and go to touch you and the charges jump from me to you in an attempt to balance out those charges, I'm not actually touching your finger. But my finger is close enough to your finger that the charges will jump, they'll arc. We still call that charging by conduction or charging by contact, ironically, even though there's no contact being made. Usually involves contact or touching, but not always. Okay? Once again, ruled by the law of conservation of charge. Touch two things together, 5 and 9, they become 7 and 7. Question? What would be an example of charging by friction? Okay, so charging by friction would be, we'll say, rubbing the balloon against your hair and then putting a balloon on the wall, right? And the balloon sticks to the wall. Charging by conduction or charging by contact would be touching somebody and shocking somebody, right? Shocking somebody with your finger. You're not taking your finger and scratching their hand with it. You're taking your finger and going and either touching the finger with it or bringing it close enough where charges will jump, right? That's charging by conduction or contact. Yeah. Yeah. Okay. Good. Yes, absolutely. That's a perfect example. When you rub your feet against a carpet, that's charging by friction. But then when you go to discharge that by touching somebody, that's charging by contact. Okay? Again, the general category is the same for both of those. It's called charging by conduction, but we often break them down into those two separate categories. This is all versus charging by induction, gentlemen. Charging by induction never involves a charge transfer. So how do we charge an object if we don't transfer charge? We'll explain that in a minute. It also never involves touching. Induction can be broken down into two subcategories as well. We call it a temporary separation of charge and a permanent charge. I got to draw pictures to illustrate this. All right, what do we mean by temporary separation of charge? I'm going to create a new page for this so I have some space to draw a picture here. Let's say that when we're creating a temporary separation of charge, we start off with an object that is neutral. Now, this neutral object, I've got it drawn with 3 positives and 3 negatives. The reality is, of course, you're going to have millions of positives and millions of negatives, and they're going to be roughly evenly distributed. Doesn't matter how many I draw, okay, the same logic applies here. It's a neutral object, equal number of positives and negatives. Let's say I bring another object nearby. It doesn't matter what the shape of it is. I'm going to draw it as opposed to a sphere, I'll draw it as a rectangular rod. Okay, this object is going to be, let's say, positive. Actually, let's make it negative. Now, I've got it drawn with all negatives, but the reality is, of course, there's still lots of positives there. There's just more negatives than positives. What's going to happen here? Well, we know that charged objects attract neutral objects, so they're going to attract to each other. We don't know why yet, but they do. We also know that there's attraction and repulsion going on here between the charges within these two objects. Tell me what's going to happen to the protons right here as a result of the attraction with this negatively charged object. Ethan? They want to pull together, right? They want to pull towards it, but they don't. They want to, but they don't. Why don't they? Yeah. Yeah, no, not so much because the electrons are pushing away. They are pushing away, you're right. That's not why the protons don't go anywhere. The protons don't go anywhere because, yeah, they're in the nucleus, and they can't go anywhere because they're too tightly bound inside that nucleus. The protons stay where they are. What happens to the electrons there, Ethan? Yeah, these electrons get pushed away over here. Now, the reality is, I'm drawing as if all of them go over there. That's not true. They don't all go over there. Okay, some of them go over there, which leads you still with some negatives over here on the right-hand side. Bottom line is, we have a net negative charge on the left side and a net positive charge on the right side. So we call a separation of charge, right? The charge is separated. Still neutral overall, right? But one side is positive, one side is negative. Why do we say it's temporary? Yes, because as soon as the object moves, good. As soon as the object moves away, what's going to happen to these protons? Nothing. What's going to happen to the electrons? They're going to more or less go back to where they were, right? Christian, question?
Oh, yeah. When they're separated, how come there's no
How can we still have positive on the left side? Because if we start it with the three positives where they are right now, then that's where they're going to stay. The positives don't move because, as Brendan said, they're too tightly bound in the nucleus by that strong nuclear force. The electrons are a little bit more free to move around, so they're going to get pushed over to the left side. They're repelled by this one right here. Now, like I said, not all of them, but because I've only drawn three, I'm drawing all of them going over there. Reality is, if I have 1 million of them in there, you know, let's say I'm going to pick a number, 700,000 go over there. Well, 300,000 are still equally scattered. That still leaves us with a net negative charge over here and a net positive charge over here. Brendan, question? No. Could you have a magnet powerful enough to pull the protons out? No, because this isn't a magnetic effect. This isn't a... Okay. No, I don't. No, you couldn't. No, I don't believe you could. No, it would have to be. Yeah, no, I don't. I'm sure you couldn't. I can't think of a possible scenario where that would happen. So another picture here. Let's draw one where you have this time a neutral object again, with the protons and electrons randomly scattered. I got three. Maybe there's 1 million and 1 million. Doesn't matter. This time we're going to bring a positively charged rod nearby. So it's positive. It doesn't mean it has just protons. It's got electrons as well, but it's got more protons than electrons. What's going to happen to the protons in this neutral object when that happens? Ethan, go ahead. They're going to stay where they are. What's going to happen to the electrons? Good. You get pulled over here to the right. Whoops. Now, like I said, not all of them. If I have 1 million drawn, then, you know, several 100,000 will go over to the right. They can't all go over to the right because at some point it becomes too full. There's too many of them over there, and they start pushing each other away, right? But you certainly get a majority of them going over there, leaving you with a net positive charge on this side and a net negative charge on this side. Now, two more things that I want to point out here with these diagrams. Firstly, that third law of the electric charge, what was it? Charged objects attract neutral objects. Charges don't attract neutrons because you can't get a separation of charge. This negative attracts this neutral because when that separation of charge is created, the sides that are closest are opposite. So charged attracts neutral because opposites attract. Positive is attracted to negative. Charge attracts neutral because positives attract negatives. Does that make sense? Positive attracts negative fundamentally, but positive doesn't attract neutral fundamentally. It's because positive attracts neutral because positive attracts negative. It's not a negative object, but it's a negative side to the object, side that's closest, and therefore it's attracted. Yeah. Yeah. Peter? Question? One more thing now that I wanted to show you with this. Go ahead, Nolan. Question? No, that's a good question. That's not the same thing as magnet at all. Okay. Now, magnetism is electrically related. In fact, magnetism is actually caused by electricity, but not in this sense. Okay, it has to be caused by movement of charges. So you don't have any, there's no magnetic effects going on right here. Okay, this is completely separate from the north and south pole of a magnet. Positive and negative are not at all north and south. Okay. Later on, you will see a relationship, but not related to this at all. Ollie? Ladies?
Electrons inside the nucleus, do they repel each other?
There's no electrons in a nucleus.
Oh, so it's
So the electrons, protons inside a nucleus would repel each other by the electric force. But remember what we said on Friday, that they also attract each other by that strong nuclear force.
yeah.
And that's over the small distances that we have in the nucleus. That's a bigger force than the repulsive force. Sometimes when we have a nucleus that's stable, the attractive force is stronger. But well, when we have radioactive material, the nucleus wants to break apart, and that's because in some cases, that's because the repulsive force is bigger than the attractive force. It's not the reason for all radioactivity, but it's the reason for some of it. Yeah. Peter, question? Your hand was up, right? Yeah. Okay, go ahead. Yeah. Yeah. No, but magnet moving relative to a wire in the right direction can be a source of electricity, but it's not limitless and it's not free. And I don't mean free in the sense of money, but free in the sense of, just set it in motion, keeps going. Because what happens there is that there's an effect that when you move a wire, this is how most electricity is generated. Is an electric generator generally when you got a wire and you got a magnet, you move one of them and it generates electricity. But the problem is that there's resistance because there's an opposing force that's formed, and we'll talk about that a lot more in our next unit, our magnetism unit. But the bottom line is, let's say you've got that magnet that you're moving relative to the wire, there's an opposing force on the magnet. So you give it a push to the right, well, there's a magnetic force on it that acts to the left. And that might not make sense to you right now, but it will later on. So bottom line is, you lose energy, quite a lot of it. So you got water coming over a waterfall, right? And it turns a turbine. So it moves that magnet around the wire, generates electricity. Well, the problem is that if you stop moving the water down to turn the turbine, then that turbine is going to really, really quickly stop on its own because of the opposing force, the force that is created when the magnet moves. If it's automatically created and you can't avoid. So it's always going to push back pretty hard. So it'll never, it's limitless if you always have something to keep turning the magnet, but it's not going to keep going on its own. You have to keep turning it, and that requires energy to do that. So that's why, I mean, look, you can generate unlimited electricity as long as you have, Peter, as long as you have unlimited energy to generate the electricity, right? Electrical energy doesn't come from nothing. Okay, it has to come from other energy. In case of the dam and the water falling down over, it's gravitational potential energy converted to electric energy, right? In case of a wind turbine, it would be the wind. As soon as the wind stops blowing, what happens to that turbine? It really quickly stops because of that opposing force acting on it. So as long as you keep pumping energy into it, yeah, it'll keep producing electrical energy, but you have to keep pumping the energy into it. Okay? Otherwise, you'd have a perpetual motion thing, right? And free energy. Okay? Make sense? Okay, this is our temporary separation of charge, and this is why charged objects attract neutral objects. One more thing here. Okay, one more thing. How do we make it permanent? No, we'd still consider that to be temporary because, you know, eventually that object, maybe you take it away and it goes right back to the way it was.
What happens if you put like electrons in there? So like I can't really compare.
Okay, if you put enough electrons in there, like way more electrons in there than protons, you mean? Okay, then you've just charged it by conduction because you've just transferred electrons to it, right? If it was independent of this, right? If you just put them in there independent of this thing being there, then okay, yeah, it's charged permanently negative, but it's because you charged it permanently negative by conduction, right? You guys ever heard of a ground wire or grounding? Or in lots of places in the world, they would call it earthing. You ever heard the term earthing? Grounding or earthing? Exactly the same thing. In North America, we call it grounding, but we're pretty much the only ones that do. A ground wire is a wire or some kind of conductor that literally carries electrons to or from the ground. I'm going to attach a ground wire to this. It's the symbol for a ground wire, but what it really does is attaches this thing to the Earth or to something really big that's like the Earth. Now what happens? Now these electrons that were pushed to the left side of this object now keep getting pushed into the ground. Now what charge do you have on this neutral object? Now it's positive, right? Because you've lost the electrons. But as soon as I take this away, it's still going to go back to the way it was, right? Because these electrons are just going to go right back. So what do you got to do before you take this away? Yeah, you got to cut the ground wire, unplug it. So that way the electrons, they may want to go back, but they can't because there's no path for them to go back, right? That's a ground wire, and that's how we permanently charge this positive by induction. Now, some of you are thinking, well, wait a second, we're still transferring charges here, right? That means it's conduction. Here's what we got to look at. I mean, that's true. There is conduction happening there. But if this is causing it, if this thing is causing it, and it's not transferring charge, then we'd still call that overall process induction. Similarly over here, we attach a ground wire. It's going to happen this time. Push the electrons down? No. You're going to suck electrons up into this neutral object. Now you got a whole bunch of extra electrons. If you take this thing away right here, what happens? They go back. But if you cut the ground wire first, then they have no way to go back. And now it's charged negative by induction. Even though there was a transfer taking place there, okay, we still call it induction because this thing that's doing the charging isn't touching it, isn't transferring. Question there, Ethan?